According to the National Electrical Code, a service is defined as the electrical supply to a building or other structure from the point of delivery. A branch feeder, on the other hand, is a circuit that supplies power to electrical equipment or other sub-distribution equipment. Based on these definitions, the service to the building concludes at the meter pack. Consequently, the circuits extending from the meter pack to the individual tenants are classified as branch feeders. When sizing conductors, different National Electrical Code tables apply based on whether it's a service or a branch feeder. Service conductors are required to be sized based on the total load of the entire building, as outlined in National Electrical Code Table 250.66. Conversely, branch feeder conductors must be sized based on the load of the specific branch circuit they serve, as specified in National Electrical Code Table 250.122. Therefore, the application of National Electrical Code Table 250.66 for sizing the service conductors leading to the meter pack and National Electrical Code Table 250.122 for sizing the branch feeder conductors extending to the tenants is the correct approach. It's important to consider that the area electrical inspector may have a different interpretation of the National Electrical Code. They should be able to provide a specific justification for their differing opinion. It is always a good idea to consult with the authority having jurisdiction, or to confirm requirements and avoid potential disagreement. If a discrepancy arises, it may become necessary to request a formal interpretation from the National Electrical Code Committee to resolve the differing viewpoints. When determining the size of grounding electrode conductors for alternating current systems, as described in National Electrical Code Section 250.66, the size is based on the size of the service entrance conductors. For service entrance conductor size 1100 copper or 1750 aluminum and smaller, the grounding electrode conductor should not be smaller than 6 copper or 4 aluminum. For service entrance conductors larger than 1100 copper or 1750 aluminum, the grounding electrode conductor should not be smaller than 3/0 copper or 250 aluminum. When the service entrance conductors are installed in parallel in 2 or more raceways or cables, the grounding electrode conductor size is based on the size of the largest service entrance conductor. If the service entrance conductors are aluminum or copper-clad aluminum, the equivalent size according to the circular Miller area shall be used. National Electrical Code Section 250.122 provides guidance on sizing equipment grounding conductors for branch circuits and feeders. The size of the equipment grounding conductor is determined by the overcurrent protective device rating. For example, if the overcurrent protection is 15, 20, or 30 amps, then the equipment grounding conductor should be 14 AWG copper, or 12 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 40 or 60 amps, then the equipment grounding conductor should be 12 AWG copper, or 10 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 100 amps, then the equipment grounding conductor should be 8 AWG copper, or 6 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 200 amps, then the equipment grounding conductor should be 6 AWG copper, or 4 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 300 amps, then the equipment grounding conductor should be 4 AWG copper, or 2 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 400 amps, then the equipment grounding conductor should be 3 AWG copper, or 1 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 500 amps, then the equipment grounding conductor should be 2 AWG copper, or 1/0 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 600 amps, then the equipment grounding conductor should be 1 AWG copper, or 2/0 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 800 amps, then the equipment grounding conductor should be 1/0 AWG copper, or 3/0 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 1000 amps, then the equipment grounding conductor should be 2/0 AWG copper, or 4/0 AWG aluminum or copper-clad aluminum. If the overcurrent protection is 1200 amps, then the equipment grounding conductor should be 3/0 AWG copper or 250 kc mil aluminum or copper-clad aluminum. If the overcurrent protection is 1600 amps, then the equipment grounding conductor should be 4/0 AWG copper or 350 kc mil aluminum or copper-clad aluminum. If the overcurrent protection is 2000 amps, then the equipment grounding conductor should be 250 kc mil copper or 400 kc mil aluminum or copper-clad aluminum. If the overcurrent protection is 2500 amps, then the equipment grounding conductor should be 350 kc mil copper or 600 kc mil aluminum or copper-clad aluminum. If the overcurrent protection is 3000 amps, then the equipment grounding conductor should be 400 kc mil copper or 600 kc mil aluminum or copper-clad aluminum. If the overcurrent protection is 4000 amps, then the equipment grounding conductor should be 500 kc mil copper or 800 kc mil aluminum or copper-clad aluminum. If the overcurrent protection is 5000 amps, then the equipment grounding conductor should be 700 kc mil copper or 1000 kc mil aluminum or copper-clad aluminum. If the overcurrent protection is 6000 amps, then the equipment grounding conductor should be 800 kc mil copper or 1200 kc mil aluminum or copper-clad aluminum. Grounding electrode system installation. As per National Electrical Code 250.50, all grounding electrodes described in 250.52 that are present at each building or structure served shall be bonded together to form the grounding electrode system. Where a grounding electrode is not present, one or more of the grounding electrodes described in 250.52 shall be installed and used. Rod, pipe, and plate electrodes as described in National Electrical Code 250.53g, a single rod, pipe, or plate electrode shall be supplemented by an additional electrode of a type specified in 250.52 or 250.54. The supplemental electrode shall be bonded to one of the following: 1. Rod, pipe, or plate electrode. 2. Grounding electrode conductor. 3. Grounded service entrance conductor on the supply side of the service disconnecting means. Equipment grounding conductor types described in National Electrical Code 250.118 for a wiring system installed in a building or structure. Metal raceways and metal cable trays shall be permitted as equipment grounding conductors. Other acceptable equipment grounding conductors include 1. Copper, aluminum, or copper-clad aluminum conductor. This conductor can be solid or stranded, insulated, covered, or bare and in the form of a wire or a bus bar. 2. Rigid metal conduit. 3. Intermediate metal conduit. 4. Electrical metallic tubing. 5. Flexible metal conduit meeting specific conditions. 6. Listed flexible metal conduit meeting specific conditions. 7. Armor of type AC cable. 8. The copper sheath of mineral insulated, metal sheath cable. 9. The metal sheath or the metal sheath and grounding conductor combination of type MC cable. 10. Cable trays, as specified in 392.3 and 392.7. Grounding path. According to National Electrical Code 250.45, the grounding path shall 1. Be permanent and electrically continuous. 2. Be capable of safely carrying the maximum ground fault current likely to be imposed on it. 3. Have sufficiently low impedance to limit the voltage to ground and to facilitate the operation of the circuit protective devices in the circuit. Sizing the grounding electrode conductor for a grounded system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. The size of the service entrance conductors is determined by the calculated load of the building. For example, if the service entrance conductors are 4/0 AWG copper, then according to National Electrical Code Table 250.66, the grounding electrode conductor must be at least 2 AWG copper. Grounding separately derived systems. According to National Electrical Code 250.30, a separately derived system, such as a generator or transformer, must be grounded. The grounding electrode conductor is connected to the neutral point of the separately derived system and to a grounding electrode. The size of the grounding electrode conductor is based on the size of the derived phase conductors. The grounding electrode should be as near as practicable to the separately derived system. Understanding ground faults. A ground fault occurs when an ungrounded conductor comes into contact with a grounded surface or equipment grounding conductor. This creates a low impedance path for current to flow back to the source. The high current flow can cause damage to equipment, start a fire, and pose a shock hazard. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock by detecting ground faults and quickly interrupting the circuit. Grounding vs. bonding. Grounding connects electrical equipment to the earth, providing a path for fault current to flow back to the source and trip the overcurrent protective device. Bonding, on the other hand, connects different metallic parts of the electrical system together, creating a lower impedance path for fault current. Bonding helps to equalize the voltage between different metal parts, reducing the risk of electric shock. The National Electrical Code requires both grounding and bonding to ensure electrical safety. Common grounding mistakes. Some common grounding mistakes include 1. Using the wrong size grounding conductors. 2. Not properly bonding metal parts of the electrical system. 3. Not grounding separately derived systems. 4. Using the water pipe as the sole grounding electrode without supplementing it with another electrode. 5. Not properly installing ground rods. Regular inspections and maintenance of the grounding system are essential to ensure its effectiveness. Over time, connections can loosen, conductors can corrode, and grounding electrodes can deteriorate. Regular inspections can identify potential problems before they become serious hazards. During inspections, check for loose connections, corroded conductors, and damaged grounding electrodes. Test the resistance of the grounding system to ensure that it is within acceptable limits. Repair any problems immediately to maintain the integrity of the grounding system. Grounding in hazardous locations. In hazardous locations, such as areas where flammable liquids or gases are present, grounding is especially critical. The National Electrical Code has specific requirements for grounding in hazardous locations to minimize the risk of explosion and fire. These requirements include using intrinsically safe equipment, bonding all metal parts together, and providing a low-impedance grounding path. Surge protection. Grounding plays an important role in surge protection. A properly grounded electrical system can help to divert surge currents away from sensitive electronic equipment, protecting it from damage. Surge protective devices, or SPDs, are designed to protect equipment from voltage surges. SPD should be installed at the service entrance and at sensitive electronic equipment. Grounding and static electricity. Grounding can also help to prevent the buildup of static electricity. Static electricity can be a problem in many industries, especially in areas where flammable materials are present. Grounding equipment and personnel can help to dissipate static charges, reducing the risk of fire and explosion. Grounding in healthcare facilities. Healthcare facilities have specific grounding requirements to protect patients and staff from electric shock. The National Electrical Code requires isolated power systems in critical care areas to minimize the risk of leakage current. These systems use special transformers and grounding techniques to isolate the electrical system from ground. The importance of proper grounding. Proper grounding is essential for electrical safety. It protects people from electric shock, prevents damage to equipment, and reduces the risk of fire and explosion. The National Electrical Code provides detailed requirements for grounding to ensure that electrical systems are installed and maintained safely. It is important for electricians and other electrical professionals to understand and follow these requirements. When it comes to grounding and bonding, there are several related concepts to understand. Firstly, impedance is the total opposition to current flow in an alternating current circuit, including resistance and reactance. A low impedance path is essential for effective grounding, allowing fault current to quickly return to the source and trip the overcurrent protective device. Secondly, fault current is the current that flows during a fault condition, such as a short circuit or ground fault. The grounding system must be able to safely handle the maximum fault current that is likely to occur. Thirdly, overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Proper grounding is essential for these devices to operate effectively. Fourthly, voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can be a safety hazard. Proper grounding and bonding can help to minimize voltage drop. The role of the authority having jurisdiction, or OJ, is to enforce the National Electrical Code and other electrical safety regulations. The AHJ may be a local, state, or federal agency. It is important to work with the AHJ to ensure that electrical installations meet all applicable requirements. The grounding electrode conductor, or GEC, connects the grounding electrode to the electrical system. The size of the GEC is based on the size of the service entrance conductors. The equipment grounding conductor, or EG, connects the metal parts of electrical equipment to the grounding system. The EGC provides a low impedance path for fault current to flow back to the source. Understanding grounding terminology is crucial for electrical professionals. The term grounded refers to being connected to earth or to some conducting body that serves in place of the earth. Grounding is the act of creating this connection. Bonding, on the other hand, involves connecting different metallic parts of the electrical system together to create a low impedance path for fault current. Ground fault circuit interrupters, or DFCIs, are designed to protect people from electric shock by detecting ground faults and quickly interrupting the circuit. They are commonly used in bathrooms, kitchens, and other wet locations. Arc fault circuit interrupters, or FCIs, are designed to protect against arc faults, which can cause fires. They are commonly used in bedrooms and other living areas. Transient voltage surge suppressors, or TVSS, are designed to protect equipment from voltage surges caused by lightning or other events. They are also known as surge protective devices, or SPDs. The grounding system should be inspected regularly to ensure that it is in good condition. Connections should be tight and free of corrosion. Grounding electrodes should be buried to the proper depth. The resistance of the grounding system should be measured periodically to ensure that it is within acceptable limits. When it comes to troubleshooting grounding problems, start by visually inspecting the grounding system for loose connections, corrosion, and damage. Use a multimeter to check the continuity of the grounding conductors. Use a ground resistance tester to measure the resistance of the grounding system. If the resistance is too high, investigate the cause and take corrective action. Grounding and lightning protection are two separate but related concepts. Grounding provides a path for fault current to flow back to the source, while lightning protection protects against lightning strikes. A lightning protection system typically includes air terminals, DAN conductors, and a grounding system. The grounding system for lightning protection should be separate from the electrical grounding system. In existing buildings, grounding upgrades may be necessary to meet current code requirements. This may involve replacing undersized grounding conductors, adding additional grounding electrodes, or improving bonding connections. When performing grounding upgrades, it is important to follow all applicable codes and standards. The grounding system should be designed and installed by a qualified electrician. Grounding in different types of buildings, such as residential, commercial, and industrial buildings, may have different requirements. Residential buildings typically have a simpler grounding system than commercial or industrial buildings. Commercial and industrial buildings may have more complex grounding systems to accommodate the higher electrical loads in the presence of sensitive electronic equipment. Grounding and sensitive electronic equipment. Sensitive electronic equipment, such as computers and medical equipment, can be susceptible to damage from voltage surges and noise. Proper grounding can help to protect this equipment from damage. It is important to use high-quality grounding components and to follow best practices for grounding sensitive electronic equipment. Finally, grounding and the future of electrical safety. As technology advances, electrical systems are becoming more complex and sophisticated. This requires a continued focus on grounding and electrical safety. New grounding techniques and technologies are being developed to improve the performance and reliability of grounding systems. It is important for electrical professionals to stay up to date on the latest grounding technologies and best practices.